Perseverance rover. Our Arduino setup is meant to simulate the Perseverance rover's pathfinding or object avoidance capability. We attached our Arduino Uno to ultrasonic sensor and servo included in our kit, and to a motor driver which is connected to 2 motors. All of these components sit on a plastic mount and look similar to the Perseverance rover. The ultrasonic sensor gives the rover a vision of its surrounding and allows it to avoid obstacles in its path. The ultrasonic sensor emits a high-frequency sound, which is inaudible to the human ear. The wave then hits a nearby object and reflects back to the sensor. The sensor then measures the time it takes from when the ultrasonic wave is emitted and to when it is received, and uses that time and the formula D equals to 1/2 times the time it takes times the speed of sound to calculate the distance. Our system uses 2 DC motor which takes direct current and uses it to rotate the motor. The motor has a permanent magnetic field across it, and the current carrying wire which produces a torque on the wire when the current is conducting. This is known as the Lorentz force in electromagnetism. We use a L298N motor driver with a dual channel H bridge to control our 2 motor. The driver is powered via 3 pins, the VS power supply pin, the VSS logic pin, and the ground pin. The VS pin can take from 5 to 35 volt and the VSS can take from 5 to 7 volts. Since we have 2 3.7 volts battery, we didn't need the VSS input due to having more than 5 volts in the VS pin. The driver can output 5 to 35 volts and up to 2 amps in each motor. The servo is also a type of motor similar to the DC motor, but it can rotate with precision to a specific angle in a shaft. The servo motor takes an analog signal from the Arduino, and depending on the strength of the signal, it can rotate to a specific angle ranging from 0 to 180 degrees. The servo has a closed loop system with positional feedback, which it uses to determine and change its rotational speed and position. Of course, we have the Arduino itself. It is a microcontroller capable of storing and executing program to control its pin. And it also has 14 digital pins, 6 capable of pulse width modulation, and 6 analog pins. The chassis we used as our mounting structure is our acrylic board that is 24 centimeters long and 15 centimeters wide. In our wiring diagram, you can see how everything is wired. The Arduino connects directly to the sensor shield. The sensor shield gets connected to the ultrasonic sensor, servo, and the motor driver. The motor driver is then connected to the DC motor and the 2.37 volts to 3.7 volts battery for power supply. The connection schematic shows the direct connection from the Arduino to the servo, ultrasonic sensor, and the motor driver. The ultrasonic sensor uses 2 of the analog pins, whereas servo only uses 1, and the motor uses 6 of the digital pins, with 2 of them being pin 5 and 6 with pulse width modulation. The code for the rover goes as follows. In the setup, we configure the servo and other pin modes, initialize the motor speed, servo, and ultrasonic sensor. The continuous loop of the code goes as follows. The servo is facing forward and takes a distance reading in front of it using the ultrasonic sensor. If the distance is too close, it backs up a little. Then it takes distance of the left and right, 0 and 180 degrees of the servo. If the left distance is bigger, it stops back up a little bit and turns left. Otherwise, if the right is bigger, similarly, it stops back up a little bit and then turns right. If left and right distance are too close, it stops back up a little bit, and that's simply it. Otherwise, if the distance was not too close, it would simply keep moving forward. We also have a MATLAB code which demonstrates the vision of the ultrasonic sensor provides. The code goes as follows. Initialize the servo ultrasonic sensor and assign required variables. Using a for loop with the incrementing variable that goes from 0 to 180, we turn the servo at the variable degree value. We read the distance using the ultrasonic sensor. If the distance is infinity, which is sometimes the case for MATLAB when the distance is too high, we set the distance to a maximum value of 4 meters. Otherwise, the distance is then appended to an array along with the angle, and then we plot the data process distance and the angle in a polar plot. This code creates a polar plot that is continuously updated as the servo moves from 0 to 180 degrees, demonstrating the surrounding area in real time, similar to a radar. There are two major problems that we encountered. The first is the DC motor spins at a slightly different rate due to the motor having a right channel higher output value than a left channel output value. This causes the rover to drift from one direction, often messing up its object avoidance and distance measuring ability. We solve this by having a delay in our code and by moving backwards after each encounter of object before turning and before moving forward. Our rover only looks left and right and turns in a completely different direction because making 45 degrees or less turns cannot be done due to the drift as well as slipping on the surface. We also have a lot of environmental and electrical noise from ultrasonic sensors data, as well as noise when the servo is turning. We solve this by using MATLAB data processing function, which filters noise and produce smooth data. Also, we delayed the timing of the servo's rotation so it doesn't happen at the same time as ultrasonic sensor collecting data. Now we will look at the demo of our rover.
So this is a demonstration of our servo controlling our ultrasonic sensor. So currently it is in the 180 degree position. When I press run, the servo begins at its neutral 90 degree position, then moves to its 0 degree position, moves back to its 90 degree position, and then moves to its 180 degree position. As a way to mimic the object detection capabilities found on Perseverance rover, we've decided to implement a live polar plot of the landscape, which takes in our position readings from the servo as well as the distance readings from the ultrasonic sensor, plotting them in a polar plot to provide a live feed of what exactly the Perseverance rover is looking at, or in our case, our Arduino rover. So based on our current landscape, we currently have our Arduino rover placed directly in front of a single obstacle with nothing else around it. So when I press play on our MATLAB script, we should get an accurate feed of what exactly the Arduino is seeing. So as you can see, our servo is spinning at a very slow rate, picking up readings as it's going. Each distance measurement is plotted with respect to the servo angle onto a polar plot. And as you can see, there is a dip in distance measurements near the center, much like how our landscape has it. Here we have another obstacle, which is much closer to the Arduino. As we can see, it is a semicircle pattern, which is roughly equally distant from the ultrasonic sensor at each angle. Based on our polar plot, we should see a similar pattern of a semicircle drawn. So as I press play, the same thing happens. Servo begins at its initial position and slowly parses through each angle and measures the position, plotting it on our polar plot. Obviously there is a noise factor in our readings, which is not very much avoidable, but with our smooth data function, we are able to get a slightly more smooth plot. And as you can see, it is somewhat of a semicircular pattern, much like how our obstacle is placed. So we will now begin the self-driving portion of our demo. As we can see, our rover is currently in front of an obstacle. Its job is to see the obstacle and turn towards a direction with the most space, which would be the right. So I'll begin by booting up our rover. And as you can see, the rover made the right decision and went towards the right. We will now do the same thing but for the opposite side. Now the most space falls on the left side of the rover. So I'll begin by booting up the rover again. The rover makes the wrong decision in the beginning, fixes itself. It's taking a while. And finally goes towards the left. Our rover also has the ability to move in tight spaces. In this case, the rover will maneuver around this square surrounded by walls and avoid hitting the walls. So I'll begin by booting up our rover again. Detects the wall in the front. Detects that wall. Detects the wall again. Moves forward. Detects this wall. As you can see, the rover is wandering on its own, filling out the entire arena without touching the walls.